Alright, so we saw the definition of impedance. So you're going to apply frequency dependent voltage, right? Frequency dependent voltage, and we're going to measure frequency dependent current, and the ratio will be called impedance. And that's the impedance analyzer basically measuring. And it will give you data at different frequencies. The real part of the impedance and imaginary part of the impedance, including the shift angle data. So you have all the data that is coming out. And frequency can be going from microhertz to megahertz. And the wider the frequency range, better off you will be in terms of, examining or collecting all the processes that I have. And the reason is that each process has different relaxation time. So some of them are very slow. Those will be captured at low frequency. And the ones that are faster, they will be exhibited at high frequency. So the more wider frequency analyzer you buy, more expensive. So that's something like that. Okay, so let's talk about some circuit analysis just to get started. So the resistor will be from the resistance symbol, and the contribution of a resistive component to the impedance is just going to be value R or on the on. And then you may have inductive component. If you do, then the contribution from an inductive component to impedance will be given by the J1 now. The J again is the imaginary. Fortunately, for most material, inductive component usually shows up as an experimental anomaly. Not the reason. Probably one of the few exceptions is zinc oxide. So zinc oxide at very high frequency can show inductive behavior in the sample itself. But for most measurement, inductive component will come from electromagnetic damage. For example, if you have a sample inside a furnace and you're doing high temperature measurement, or most ceramic, high temperature that you have to measure, and the lead wires are coming out of the furnace. And if these lead wires are not bent, and if they're sagging, then you will get this electromagnetic induction that will show up in your impedance value that you measure as a component L. So you will need to use L as a subject. That's not really a sample behavior. You don't really want the L, yeah? How can you get rid of this? Well, one way that you can do it, you can take, for example, the two-board balloon napkin. It has two holes. And the value of these went through those holes. And make sure that it's straight and parallel. And that they're not sagging. That's one way to get rid of your inductive component that is coming from an experimental line. There are the things you can do. You can write the sample of platinum connection to get rid of some of the other experimental anomaly, but let's not get into those right now. And then if you have a capacitor will contribute to the impedance then by this equation 1 over J omega C. And you will actually see. I think there is a source for where this comes from. Excuse me. So that is electrical charge given by C times C, right? That's correct? Capacitance and voltage. And current is going to be dq, buildup of charge as a function of time. Right? And I'm now applying, I'm going to assume that capacitance is constant over the terminal, which is not always the case. So C, and then I'm applying a frequency dependent voltage, which was J omega t. So my voltage has an amplitude and the phase that is changing frequency. So if I calculate dq dt, I'm going to assume the C to be constant, so you can see that dq dt will be what? C times V naught exponential J omega times J omega. Is that correct? If you take the derivative. Okay. All right. So this is what we get out of this. And then your impedance will be I over V. So your I is CV0 exponential J omega t. This is really V. And then you would still have multiplied by J omega. Right? And you see that this is V voltage. So that will cancel with this V. And the answer you get is J omega times C. Is that correct? So the something called must be V over R. V over R. So this definition is wrong. Oops. Yeah. So this is V over R. So just the reverse of this, inverse of that will produce this, which is 1 over J omega C. Anyway. So I hope you got that. So I made a mistake initially. Instead of I as V, it would be V over I. So you'll get 1 over V over. So that's how that the impedance contribution coming from a capacitor will be that quantity. Okay. Anyway, so that's what you because we're going to measure the impedance. That's it. Okay, so let's do some simple electrical circuit analysis. We have an R and we have infinity, right? Sorry. R in series with a capacitor. The contribution from this will be just R. And contribution from this will be 1 over J. So just the overall impedance will be the same as R plus 1. If it's parallel circuit, then it's going to be 1 over the effective impedance. By the way, sometimes you'll see that I put a star. Sometimes I don't. But it means this time it's a complex number. So it will have real part and imaginary. That's all. So 1 over impedance will be 1 over R and 1 over contribution from this one. So 1 over that will be just J omega. It's a parallel. Okay? And then if you do just a parallel circuit, this is what we saw, that effective 1 over impedance with 1 over R and 1 over contribution from capacity for that. Simplifying. Now, we are interested in impedance. Impedance will be simply inverse of that. This is going to be R divided by that. This is right there. Now, all you have to do is, you know that this is a complex quantity, so you need to separate the real part, which is the denominator. And the way mathematically we do it, you have to multiply the numerator and denominator by the complex conjugate. You have to multiply the 1 plus 1 9 your way out. And if you do that, the denominator of everything is equals A plus IB times A minus IB, which is A squared minus B squared, I squared, that I squared is negative, so you get a positive. And the numerator will be right there. Now you can easily separate the real versus the imaginary part. So this will be the real part, and this will be the imaginary of your impedance. And this is exactly the calculation you repeat cell like this, and ultimately giving you, at each of the frequencies, giving you the so-called C prime, which is the real part, and the C double prime is the imaginary. And you can see those are going to change as you change frequency. So different frequencies get different Z prime and Z double prime. So overall, your impedance of your sample will be given by this. But this is the Z prime, and this is the Z double real part and the imaginary. Now you can, for a parallel circuit like this, you can actually show that this Z prime real part and the imaginary part will be connected by a relationship that looks something like this minus R over 2 squared, plus this squared will be equal to 2 squared, I squared. Can you imagine what kind of shape equation will be? Have you ever seen this kind of equation before? Something like this, x minus a squared plus y minus b squared equals r squared. On the next line plot, what shape would this be? That's exactly what it is. This is an equation of a circuit, and equation of circuit, as you can see, that the center, that circuit will be on the real axis. It will be at a value of r over 2. On the imaginary axis, it will be at a value of 0. And the radius of the circle will be r1. So you can represent this on an impedance plane plot. Then obviously I did not draw the full circle. I drew only half the circle. Do you know why? It's an equation of circle. Why is it going half the circle? There must be a reason. So you will see that if you draw the full circle, it will have things like negative impedance, which has no physical. So this circle of this equation is valuable with in the first quadrant. Okay? So in other words, if you plot the real impedance versus real part of impedance versus imaginary part of impedance, or Z double prime versus Z prime, you get the semicircle. And in fact, the diameter of the circle will give you exactly the R value that you can beat 100 over more. 5 kilo ohm, or 5 mega ohm, whatever that bandwidth is. And then you can go to the peak frequency, so you can actually look at your data and you can find where this circle actually peaks and what frequency would be 100 kilohertz. So at that omega 100 kilohertz times C times R has to be equal to 1. This is the mathematical condition that will come with circuit analysis. If that's true, then you know whether you know R. You already know the peak frequency of device. In total, this function compare that. What are we doing by doing this circuit analysis and doing this so-called impedance strain part? We are getting numerical values for the circuit analysis that we're using to describe our. And for a simple single phase, maybe single crystal material, this can be resistance of your sample and the capacitance of it. Simple. So you can see that by doing this kind of circuit analysis and the impedance strain part, ultimately you're getting numerical values for the circuit elements that you are using to represent the behavior. So that's all you have to do is get numbers from picking your experiment. And you see that these numbers will help you because now you're going to associate this circuit analysis with material excitation. And you're going to associate this R with something, you see with something, etc. And the product of this R and C will give you the relaxation kinetics. So if you know what the C value is, what the R value is, take the problem. And then you'll see that, in fact, I have a slide here. Now, okay. So this plot is usually known as a group. For instance, maybe a sort of 9-digit plot. A 4-pole plot. See already here. For the name of the expanding investment. So, when you hear about 9-digit plot, a 4-pole plot, that's exactly what. Or an RC panel, it will look like this. So that's your circuit for that. And there is something called Bogey effect, by the name of Bogey, who happens to be at the hospital sometimes. So, anyway, if you plot on the other hand, the modulus of this quantity is defined as the Z modulus is defined as that quantity defined as square root of the real part of the impedance, Z prime squared plus Z double prime squared. So basically take the real part squared, add it to square root of the imaginary part, take the square root, define the quantity called modulus of the impedance. And if you plot that quantity on this axis, logarithm of that one, as a function of logarithm of frequency, it will look like this. Vector, and then an inclined linear part. And if you extend it all the way, thank you. You keep on forgetting. If you plot that logarithm of that one, that is just the one on this axis, and logarithm of frequency of your measurement on this axis. That log V will look like log 2 and that linear part. And that plot only gives this R, which is exactly the same as this R. And if you extend the linear part, and the intersecting point will be equal to 1 over C. So you can get C from these in the spectrum. And that C should match with this C that you get on the night visible. So why do people even need voting one? No, first, you can see that, depending on the data, by the way, as you change frequencies, your data will be lying along the periphery of this solution. And you see real data will be scattered. It may not lie on the perimeter of the solution. It depends on the quality. And you have to do a non-linear distance by fitting your certain equation of such. But your data will not, unless I understand the idea. If you do body along similarly, your data will lie along this lateral entity. So the difference between the nitrous plot and the body plot is that depending on the data will fit much better on the nitrous plot or much better on the body. So the quality of data, if you use both, try to eliminate some uncertainty in the experiment. Because in either case, you're fitting a circle, you're fitting a linear, constant part here. But if you do both at once, the physics is the same something. So the R value we get from here and the C value that we get from this frequency match with R value that you get from the body plot and the C value that you get from the extension of the little match. Because it's the same time. Okay? Okay, the other advantage of the body plot is that you can actually plot the shifting the data that impedance analyzer will give you that as a function of log of frequency. It will look like this. And that will actually help you determine the peak frequency where that peak frequency exactly has the frequency, right? And again, because of the uncertainty, you will not be able to exactly figure out what the peak frequency is. But your body plot will give you a much better idea what that peak frequency should be. This nitrous plot and body plot should be used complementing each other. The both type of analysis will help eliminate some of that stuff. So again, you see, in real statistics, we talk about nitrous plot, plot, body plot, so that you know. If you look at the dimension of R times C, which is called relaxation time, you see that dimensional analysis tells you that the dimension of that product will come on this time. And that's why it's called relaxation time. So if you take your R value and take the product and C value in the right unit of it, it will give you dimension of time. We use this kind of relaxation time in many fields, including dielectric observation. If you have dielectric field, internal dipole, and when you apply that field, your dipole will start orienting on the direction of applying the field. Does it happen instantaneously? It doesn't. So you can see that as soon as you apply voltage, many of them will align almost immediately. But some will have to reorient and will take some time and eventually come to the saturation polarization. And this rate will determine what this how should be polarization done. And I'm showing you some of this from the dielectric literature that you can model this by this dielectric observation. Okay. Anyway, it's very similar concept here with the relaxation times. Represent the speed of the process, how fast how slow. Okay, so we talked about RC path, and we know that give you a sense of this impedance getting blocked. Well, what if you have an R component, connected in C, and the effect will be simply the sensor will shift by a certain amount, and that shift value R1 will represent that, and this will still be the diameter will still be this R in the parallel system. So you can see again, you're getting one R, R1, R2, and then from the peak frequency, you're going to get C. So again, the idea is that by doing this nitrous plot or pull plot, you want to get numerical value for almost everything. Okay? And I think this kind of circuit is actually used in corrosion. As I told you, one of the first communities that used this technique very successfully was the corrosion. So if you look at the corrosion of a bare metal that is inserted in a solution, okay, and that can be represented by the circuit, exactly same circuit. Okay? RC parallel connected to a CD power. And in that particular case, where you have a metal that will be corroding because of the reaction interface of the metal inserted in the solution, that R will represent the resistance in the solution, which is an electrolyte. Okay? So that's basically the resistance of the solution. This C will represent the so-called double barrel capacity. So when you insert a metal in an electrolyte, there will be charge distribution that will create at input, and that gives you this double barrel capacity. Okay? So that will be this, and this RT will be the exchange current or exchange between the metal and the electron. And there is some barrier which is represented by this resistance, which is referred to as polarization. This is what corrosion community needs. And from the impedance measurement, they can get numerical values for all. And once they get RP, they're very happy. They will say, depending on whether RP is large or small, that will determine the corrosion of the patient. Very, very important. You can see in real life, people are using this kind of circuit to get the physics out of it. I'm showing you some of the simpler examples, but I'll show you a little bit more complex and circuit analysis one of the circuit is very similar to what we already did. The way you do is you do the parallel part first. That's 1 over parallel 1, which is going to be 1 over R, T. And from this you'll have 1 over J omega. Remember that concept? The contribution from a capacitive component to T. So you can simplify, keep going. So your parallel part will give you this. Where you have already separated into real part and the imaginary part, the way we did last time. And all you have to do is now add the series partners. So the overall will be that to the electrolyte resistance now to series is added. Okay? Now you can see that on an impedance length plot, this will look something like this. So your experimental data will lie along this perimeter of that study circle, but the same circle is not shown because this RS is connected in series with the RC curve. So now you can see that you can figure out what the RS value will be, what the RP will be, which is R. And from the peak frequency, we get the C double with capacitance. We should get all the three numbers in that circuit. If you look at the voting plot data, voting plot will give you a plateau, an inclined line, and another plot. Okay. And so one plateau will give you RS. This will be RP. And the extension of that linear part will give you CW. So either from the Nyquist plot or focal plot or the voting plot, you get all this important values. And corrosion community is particularly looking for art because RP will give them an idea of what is the corrosion kinetics of corrosion. Life can get really complicated. This is a model that corrosion uses. The corrosion of the metal with porous insulating foam. So if you have something like aluminum metal, and then if you grow an oxide layer, protecting layer, aluminum oxide, and then you insert that into the metal. So, aluminum protected by that pattern layer, aluminum oxide. But if it's a thin foam or some porosity in that aluminum layer, your metal will actually corrode. You have to like will shift that or and metal will start falling. For that kind of scenario, they use this one. See how confident our future? So now you have, this is something that we already analyze. But on top of that, we have a seam paradigm and then another RS seam. And, physical interpretation of this is still the electrolyte resistance. That RCT is still determining the corrosion polarization of the polarization resistance charge structure, CT. That's really determining the corrosion rate. And this R will represent the porosity related resistance. And the speed on layer is still the same one at the interface of the liquid medium of the sample. And this speed down is the capacitance for coating, capacitance meaning the capacitance of the lower half. You see, the circuit that you are picking is physical deep. So, the current is using the circuit to get the linear. But mathematically, you could do the different circuit. It was this. So they actually verified whether some of these are made. For example, they can change the coding. In that case, this value should change. They can change the size of the porosity, for example. In that case, this value will change. That's how they can verify that this is a realistic physical model that is representing a set, rather than being an arbitrary circuit that happens to fit the thing. And I'll show you an example where you can choose at least 3 different circuits to fit the same. So the question is, which one is correct? If you go to the correct committee, they will say, this is the correct one, because I can verify it by making changes in myself. So that's the beauty, or that's the consequence of material science. And these are not arbitrary. These are the real meaning that you should, or you can represent yourself. So if you do the circuit analysis, do your math, and do the impedance plane plot, imaginary impedance versus basic, like shift it doubles to myself. You can see you're getting to how many R do you need? 3. You will get 1 from the step. This diameter will give you second hour, and that time it will give you third hour. And you need two capacitors. One will come from the peak frequency analysis of this one, and the other one will come from the peak frequency analysis of the other. So again, you will get VR and 2C. And you will get numerical values that you're looking. And because they have physical meaning, what they represent. If you want to get this from body plot, it will look even crazy. You can see that plateau, linear part, another plateau, a linear part, and another plateau. And this three plateau will give you 3R. So RS, RPO, porosity, and RCT, which is corrosion. And then from the extension of the two linear parts, you will get the 2C. Same thing, whether you do lightness plot or body plot, the ultimate goal is to get numerical values for the circle that is specifically. Is that making any sense to you? So this is what the game is all about. But the question is, we have to play a fair game. Play an unfair game with getting unfairness, it will be usually wrong. In fact, if you look at the CP spectroscopy related literature, at one point the estimate was more than 50% was wrong from this circuit. Because they simply pick the circuit either the light or the one that propagates some model, but they never bothered to verify that circuit would be present the sample date. So obviously it's going to be wrong. And there's a lot of wrong literature. So when you're reading this literature, make sure you have that suspicion. Okay, so but the light out is don't get it. It's an ideal semicircle or ideal polygon and so on. You get something like, people use the so-called constant phase element. Constant phase element is like neither a pure capacitor nor a pure resistor. So it was some hodgepodge picture. So this constant phase element will yet distort meaning. You see it in this case, I'm drawing something that looks like the semicircle, center of the semicircle is not lying on the real axis. It's actually lying on an axis that makes an angle. So your semicircle gets depressed. It's not, the center is not lying. Sometimes you will get not only depressed semicircle, you will get skewed, as if you have put your semicircle on one side, on this side or that side. Skewed semicircle. And sometimes you will get linear behavior. Some data will be different, straight line. And typically, this can be associated with fusion. Related gradually instead. Something like, let's say you take your strip like zirconia, which is an oxide in the metal, and you put a platinum ink as a lead. Platinum ink, you have to cure it, it will burn out the organics and so on. Then you will get a porous layer. Okay? And where ideally you want platinum particle connected that with a lot of silicon. Why do you need that? You need all this porosity for oxygen to be able to come in with the so-called triple point TPP. TPP meaning is that, for your oxygen fuel cell, oxygen sensor, oxygen pump, etc. for those kind of applications, you need, so you have your Y is Z, heat transferable zirconia, which is an electrolyte. And then you put this porous platinum, and at this interface, on one side you supply air, oxygen as the source for a fuel cell. On the other side you'll be supplying fuel, like hydrogen, or some sort of reformed hydrocarbon. But at this interface, what will happen is that it will grab this oxygen from the gas phase, oxygen molecule, and then it will combine with electron and form this two atomic oxygen ion. And then this oxygen ion that you generate by this so-called oxygen reduction reaction, And these species that you generate will be able to move through your YSZ, because YSZ is an oxygen ion. Remember we talked about this group of beta? Because that there is a large range of CO2 where this material will remain as a 100% oxygen ion, and that's your electrolyte here. Okay. So you can see that for this oxygen reduction reaction to happen, where does it happen? Happens at the triple phase boundary, TTB. Triple phase boundary. Well, what are the triple phases? One phase is your solid YSZ, other phase is your platinum, and the other phase is going to be the gas phase. So wherever this porous platinum is in contact, so it's you have a particle of platinum on YSZ porosity. So wherever the platinum and YSZ is meeting with the oxygen molecule, that's your TTB. That's where this reaction is happening, which is the most important reactor in your device. Okay? You can see that you need this porosity so that the gas molecule can get to that TTB, right? So depending on what kind of platinum heat you have used and the type of heat treatment you use, the porosity may be very, very high. And if the diameter of your holes or core is going to be comparable to the diameter of the molecule, you know what can so the diameter of the core is comparable to the diameter of your oxygen molecule. So-called Wilson effect. Your oxygen molecule, get to TTB will be bouncing by the wall of your. On the other hand, if the porosity is large compared to mean-free gas, oxygen will quickly get. So depending on what porosity size you have in your platinum, pure platinum heat that is sitting as an electrode on that thermal device, there may be a rate limiting step for oxygen to get to TTB. And for those kind of scenario, you will get a straight line in your impedance. And people can actually, from the analysis of the straight line, they actually get diffusion of oxygen molecule through that restricted pathway. Anyway, so all kinds of complications that show up in real systems. That's all good. trying to show you here. And so, people, since they cannot associate, some of this behavior with the purely capacitive component and the purely resistive component, they use this large quantity of constant phase element. The constant phase element, for example, impedance coming from that element can be given by some constant times j omega, the exponent negative. And the P will be somewhere between 0 and 1. So if P is 0, the capacitive component or constant phase element contribution to impedance will be simply constant. Real value. So this would behave like a resistive component, resistor. Because in resistor you have only the real value. There is no imaginary. On the other hand, if P is 1, you can see that this will be some constant over j omega. You can see that remember that from a capacitive component, the contribution you get is 1 over j omega. So this was looking like contribution from a capacitive capacity. So if P is close to 0, the constant phase element is like your resistor. If it's close to 1, it's acting like a pure capacitor. What if it is 0.7? It's more capacitive than this. So people use this constant phase element, and for a sinusoidal applied voltage, you can calculate or model the contribution of the constant phase element to be impedance by this relationship. Again, you see this P and P. So depending on P value, it will be close to a real resistor or real capacitor or P. It's just one way of this is if P is somewhere some big, between 0 and 1, some big value, it will represent the degree of GP capacitor in dynamic. So these are type of things people use in behavioral analysis. The other thing I wanted to emphasize is, again, so what we learned is that sometimes you can get depressed semicircles, skewed semicircles, sometimes you get straight line. They have physical implications. For example, remember I said that we have a depressed semicircle. The center of the semicircle is lying on an axis with an angle from the real axis. So this angle, depending on how much of deviation, can represent heterogeneity in the microstructure of itself. For example, you have polycrystalline sample, and you have huge large grain size distribution. That will be reflected in making the sample larger and larger. On the other hand, if you create a microstructure with more or less uniform grain size, so the grain size distribution varies in a very narrow. That will be a kind of the homogeneous microstructure. The angle, this deviation angle will be so meaning that your center of the semicircle will really lie on the real axis. So people use this deviation to sort of get an idea of how heterogeneous microstructure is. And you can verify by changing the microstructure to see whether that kind of interpretation is correct. All right, the other thing I'm going to emphasize, and I'm going to finish it in the next 5 minutes, is that, I talked about this impedance plane plot, like in Rice's plot, body, and so on. You can analyze the data in other contexts, like at meters. What is a meters? It's just inverse of impedance. So your impedance analysis gives you a impedance vector. You take the inverse of that, that will give you admittance. You can create admittance and then plot imaginary part of admittance and real part. That will be called admittance plane plot. You can do electrical models. So you can see how to convert. So if you have impedance value, all you have to multiply by K omega. That will give you electrical modulus. So you can convert your impedance to electrical modulus and plot imaginary modulus versus real modulus and create a plot called modulus plane plot. Or you can analyze in so-called capacitance plane plot. You may get converted, create from impedance go to admittance, multiplied by 1 over K omega, that will give you capacitance. So all I'm showing you is that you have a choice. You would say 90, maybe 95% of the analysis is done in impedance. But once in a while you see people that can do admittance plane plot, modulus plane plot, and capacitance. And you will see that multi-plane analysis and sometimes give you physics that is not revealed in one of them. I'll show you that. So again, remember that there is an advantage of doing this on. I'm going to show you some circuit that will look or plot different plane plot that will look identical. You have to look identical. Let's check that some circuit. But depending on what plane they are, so this is the impedance plane. That's your RC parallel connected with series that we have done. If you see this in an impedance plane plot, if that's on circuit, it will be completely different combination circuit elements. Still capacitance, this is now conductors, which is 1 over R. Okay, this conductors. If you see this in capacitance plane, same shift transfer. Look at the circuit, right? Very different. Modulus plane. So depending on which plane you see this, you'll coming up with different combination of circuit elements. That's something obvious from the math. And here is one of the punchlines that coercive circuit is not unique. And I'm going to show you this out of Prof. McDonald's book. So you can fit the same paper by one of this circuit arrangement known as what? 3 RC parallel connected instruments. This is a very popular model for ceramic metal because you can associate one of this with grain, one of this with grain boundary, and the third one with the interface of your sample and reactor, which is called electron symmetry. So this makes sense. Something is moving here on the instrument sample, like oxygen ion, and then, in YFE, and you're saying that oxygen will have certain relaxation time moving through the grain, across the grain boundary, and across the sample electric, and they're connected in series. Makes sense. Okay? You can take the same thing, right? But this one. This will, so-called Maxwell model, this will have completely different. Okay, or you can use this one. Same data can be fit by one of these circuit elements. So which one should you use? You obviously, if you're a ceramic material person, you will probably be tempted to use this because it seems to match with your physics. But an electrical engineer may come or a modeler may come and say, oh, This one fits it. So why should we be using this? For a third person will say, no, this fits very even better. Why should we be using this one as opposed to? And this is where you come in. You say, I can make changes in myself that will have impact on individual parts that I can relate. For example, if you take your YLC and filter it at different temperatures, 1200, 1500, 1700, the three times over, the three different ratios of grain to grain out, and the impact you should see on the grain point component. And if you do see, then sure, indeed, this one is a defective grain point, average grain point. Or you can change electron. You can make contact with platinum. You can make contact with gold and see whether this component is changing. So this is, for material science, it's okay that you can say, I know exactly which model correct and I can verify like the corrosion behave very well. So this is how you get rid of this problem, not having big jobs. So you can make it easy. That's the point. And this is important because otherwise you'll be practically wrong in fact. And I think I'm going to end with this one that illustrates some multiplying. So here's an example of this is really when the certificate of the imaginary and real. So this is really deep. See, very nice looking single sensor idea. With the center lies in the real. No heterogeneity. Okay? And this number you see, 1, 2, 3, 4, 5, 6, there's a frequency that is 10 to the exponent 1. So that's 10 hertz, 100 hertz, kilohertz, etc. You're going from low frequency and high frequency. Okay? You look at that and you say, oh, I have the system where I have one R and a C pair. That's it. Single illustration. Okay? If you take that data and convert it to electrical models and do the modulus split plot, see? Very nice looking two sensors. It's okay. The model split plot is saying, no, you don't have a single relaxation beam. You have two relaxation. What is happening in this here? Why does it resolve very clear? Why doesn't it resolve here? What do you think? It all depends on the actual value R1C1 and R2C2. So in fact, one of the semicircle is hiding either at the high frequency end here or the low frequency. So the semicircle is so tiny when plotted in the impedance plot that it doesn't quite appear. And then when you convert the data into modulus, it reduces it. Does that mean you have changed the physics? Of course not. All you are doing is by checking the data in another plane, you are confirming something that was not clearly revealed in the impedance. Well, you can get the opposite. This is simulated data. You can see that in the modulus plane, single semicircle, but in the impedance plane, it's so depending on R1C1 and R2C2, the extra physics may be revealed in one, but not in the other. That's why a careful experimentalist would at least check an additional coefficient. So if you're doing impedance plane work, you should check the capacitance coefficient. If you're doing admittance plane work, you should check the modulus. No, I'm sorry. The other way. Impedance plane plot, check with the modulus. If you're doing admittance, check in the capacitance plane plot. to see whether there are any additional differences. Okay. So this is the small here. I'm going to stop here. Let's look at an interesting figure. And just simple examples will be like if you take something like variant isomet or 3 or 4 components instead, your circuit will not look as simple. But at least I'm trying to clarify the physics and I'm showing some real life examples from here on. So this is really the fundamental basis of analysis. And I'll see you tomorrow at the same time.